Okay, so finally, let's talk about the solid state. So we talked about gases mainly last semester with the gas laws, and then we've talked about a lot of properties about liquids just now, and so we're going to just take a little time and look at solids. So we know that solids are nearly incompressible. They're very well defined. They take their own shape. They don't fill to take the shape of the container. And we know that the solids are in close contact with each other and in fixed positions. Um, so solids are also characterized by the type of force holding the structures together. And some of the ones that we've already talked about, polar, nonpolar, London forces are there, but there's a few other forces holding solids together. So the ones that we've already talked about are intermolecular, like London dispersion, dipole-dipole, hydrogen bonding. But there are some other forces in solids that are not in liquids, and those are actually intramolecular or chemical bonds. So we need to include those when we're talking about solids. Okay, so there are four types of solids. There's the molecular, which are mostly the things we've been talking about, the things that have intermolecular attraction. So those are things that have dipole-dipole, London dispersion, hydrogen bonding forces. So things like water, carbon dioxide, etc. Those are molecular solids. Then we have metallic solids, which are made up all of metal, like one or two kind. It could be more than one kind of metal, but all metals, and that would be a metallic bond. And then we have our ionic compounds made up of a metal and a nonmetal stuck together. So all of our salts and things like that, an ionic bond. Ionic is another kind of solid. And then finally, covalent bonds, things like diamond, carbon, coal, things like that, things that only have covalent bonds. So these are four different types of solids. Okay, so the first one is the molecular solid. That's a solid made up of atoms and molecules held by intermolecular forces. And again, these are the hydrogen bonding, dipole-dipole, London dispersion. So lots and lots of solids are of this type. Things like solid neon, solid water, which is ice, solid carbon dioxide, etc. Here's some molecular solids: solid hydrochloric acid, solid dry ice, solid water. So if you freeze alcohol, if you freeze gasoline or anything like that, these are all molecular solids, things that have intermolecular forces. Okay, so a metallic solid is a solid that consists of positive cores of actually nuclei held together by a surrounding sea of electrons, so a metallic bond. So you've got the nuclei all sort of held together or kind of in position, and then the electrons kind of move between them. And this is the reason why metals can be electrically conducting, because the electrons are free to move between metals. Some examples are, things like iron, all the metals that we know, iron, copper, silver, and they can also be alloys such as brass, which is an alloy of copper and zinc, or bronze, which is copper with usually aluminum or manganese, something like that. Or like gold is a very soft metal, and so we can have an alloy of gold and silver that form, like 14 karat gold will have a lot less gold in it than say 24 karat gold. And so it's an alloy with other metals. Anyway, metals. And so these are pictures of metallic bonds. And you can see the positive nuclei, and then the electrons aren't really associated with any particular nuclei, but they're free to move. And you can sort of see in the upper right-hand corner, those electrons are moving around. And so that's why we can have, why they conduct electricity, an electron sea. Okay, now an ionic solid, we've spent a lot of time looking at ionic solids. Those are solids consist of cations and anions held together by ionic bonds, opposite charge. And of course, our examples are any kind of ionic compound that we've talked about: sodium chloride, zinc sulfide, cesium chloride, any kind of ionic compound. And so here we have some examples of those. So these are with ionic bonds. Different zinc sulfide and sodium chloride, etc. And then finally, the fourth type of solid is called a covalent network solid. And this is just a bunch of atoms held together by covalent bonds. And we haven't talked about strength or anything, but these tend to be the strongest. These are things like carbon in its form as a diamond or as graphite, quartz, glass. These are all covalently networked solids because all the bonds are these strongest covalent bonds. So here's some pictures of covalent network. A diamond is just a bunch of covalently bonded carbons to each other. Graphite actually is covalently bonded carbons as well, but they're not in that tetrahedral form that we see on the left. They're actually in sort of sheets that can slip and slide next to each other. So that's like your pencil lead is made out of graphite. You can see here quartz is silicon dioxide that's very, very organized, very strong shape. And then we have like silicon dioxide glass is an amorphous, but they still are all covalent compounds. So this is just sort of a summary, molecular, what are the structural units, what are some examples, what type of forces do we have, and just the examples. So physical properties of solids, many of the physical properties are attributed to its structure and to its attractions. And very similarly to how we compared liquids, we can also compare solids. So things like the melting point of a solid, the hardness of a solid, the conductivity of a solid all depends on the type of structure we have. So let's look at melting point and structure. So in general, for a solid to melt, the forces have to be overcome. So we've got these things holding molecules together, and they have to be broken. So for a molecular solid, because this even includes hydrogen bonding, dipole-dipole, and London dispersion, they're all fairly weak forces. And so molecular solids tend to have very low melting points, which means below 300. Metals can have very high melting points, but there is a lot of variability, so I couldn't really ask you anything straight out, but they tend to have high melting points, as you probably imagine. For group 1A and group 2A metals, they tend to be low because those are softer metals and they're much more reactive. As you move into the transition metals, the melting point will increase quite a bit. And then the elements in the middle of the transition metals will have the highest, so things like iron and manganese, chromium, etc. Ionic compounds and covalent compounds, because they have the very strongest type of bonds occurring, tend to have very high melting points. Ionic solids, it will depend on the strength of the ionic bond. So it will depend, I think we'll talk about this in a minute, it depends on the charge of the ions and how strong that bond is. So if you have like NaCl, which is a positive one and a negative one, will have a weaker attraction than, say, MgO, which is a positive 2 and a negative 2. So the magnitude of the charge will make a stronger bond. So the higher the charge, the stronger the bond. And then the size of the ion will also matter. So the smaller, so like magnesium would have a stronger attraction than, say, calcium, because calcium is a bigger molecule or bigger ion. So the smaller the molecule, or smaller the ion, the stronger the attraction. All right, so if we look at this, you can kind of get a good idea. So the first three, actually the first few, the first 5 are all molecular attractions. Neon being dispersion, the very weakest type of attraction, has very low melting point and boiling point, as we know. We talked about that already, but let's look at the melting point. Hydrogen sulfide, which has dipole-dipole interactions and also molecular, you can see is higher than the London dispersion, but still pretty low melting point. Chloroform is also polar, has a low melting point. Water has a low melting point. Acetic acid is a little bit higher. So molecular depends on the attraction. The more hydrogen bonding there is, the higher the melting point, but still relatively low compared to some of these others that we'll see. As we can see, we've talked about metallic being much more random, and so the mercury actually has a very low melting point. Sodium is kind of higher, but then you get to something like tungsten, which is in the transition metal, and it's got very, very high melting point. And then we have our ionic compounds. And what you might notice is cesium chloride, which is a +1 and a -1, has a lower melting point than NaCl, again +1 and -1, but because sodium is smaller than cesium, that bond is a little bit tighter, and so that's why sodium chloride is higher than cesium chloride, because sodium is a smaller ion than cesium. And then if you compare sodium chloride to magnesium oxide, like I said, sodium chloride is +1, -1, and then magnesium is +2, oxygen is -2, so that is a much stronger attraction, the +2 and -2, so that's why it has a much, much higher melting point. And then when you get to the covalent network, they have very, very high melting points. So again, I couldn't ask you something mixing apples and oranges, but I could ask you which one has the higher boiling point and give you, like an ionic compound where it's +1, -1, or +2, -2, or size. Or I could ask in general between molecular, ionic, and covalent. And so we can do sort of the same things that we did with the liquids. So we can look at hardness and structure as another property. Hardness depends on how easily a unit can be moved relative to one another. So how hard is it? Again, molecular solids that have the weakest intermolecular attractions tend to be very soft compared with ionic compounds where forces are much stronger. Covalent network solids are some of the hardest compounds out there, things like diamond, silicon, glass, because they have such rigid covalent networks. Yeah, again, diamond and silicon carbon are some of the strongest, hardest materials known. So again, molecular solids tend to be the very weakest and softest. Ionic tends to be much stronger, harder substances. They're also very brittle, and then the covalent is the most solid. Again, hardness and structure. So molecular ionic crystals tend to be brittle because they fracture along these planes. So that's something to keep in mind. And then metallic solids tend to be malleable, which means you can make them into sheets, or ductile, which means you can roll them into one. A couple other properties about solids: electrical conductivity. Molecular and ionic solids are generally considered non-conductors. You might say, wait, ionic solids? Yeah, they're not really. Only they are very conducting when they are dissolved in water, but they're not very conducting when they're in their solid form. Ionic compounds in their molten form will conduct, or also in their dissolved form, but not in their solid form. Most metals are considered conductors because those electrons are free to move. And so this is sort of a summary. Melting point, molecular low, metallic variable, ionic high to very high, and covalent very high. Hardness and brittleness: molecular tends to be soft and brittle. Metallic has variable hardness but tends to be malleable. You can make it into sheets. Ionic tend to be very hard and brittle, and then covalent very hard. And then you can see electrical conductivity. Molecular are non-conducting, metallic are conducting, ionic are not conducting as a solid but conducting as a liquid, and covalent are generally non-conducting. And then finally, solids can be either crystalline or amorphous, and we saw that a little bit before. A crystalline solid has very well-defined ordered structure. For example, sodium chloride is a crystalline solid. Sucrose is another crystalline solid. An amorphous solid is one that is disordered and has no well-defined arrangement, sort of like glass. A lot of A crystal lattice is just a structure. Where your textbook goes way more into crystal lattices than I'm going to get into, but you should at least have an idea of what a crystal lattice is. And then a unit cell is a part of a crystal lattice that D is actually a unit cell. So if you take a unit cell and you line them up, you get the whole crystal. So you can see that a unit cell is just the smallest box-like unit where you construct the crystal by stacking them all up together. But a crystal lattice is very geometric and very structured. Again, we're not going to get into this, but you can have very different shapes for crystal lattices. You can see cubic, tetragonal, orthorhombic, depends on the angles and the length versus width versus height and such. So there are definitely different crystal systems, and these are not just metals, but they can also be ionic compounds. And then there are some different, within the unit cell, you can have different shapes, like a simple cubic versus a body-centered cubic versus a face-centered cubic. These you can see on the next slide. Simple cubic is just the corners. Body-centered has one more in the center, and then face-centered has one on each of the faces of the box. Again, we're not going to get into this very much in this class. And then just again, how do they know all of this? Well, you can use something called X-ray diffraction to determine the structure and dimensions of a unit cell, because so they know the length, the width, the angles, and things like that by using X-ray diffraction. So let me just describe that real briefly. You can then, X-ray diffraction can help you figure out the size of a crystal, etc. And this is actually the way that they figured out, using X-ray diffraction is how they figured out what Avogadro's number was, because they were actually able to figure out the size of a molecule and an atom, etc. way back then. Anyway, what happens is that X-rays are shot at a compound, and then depending on the plane of the crystal, the X-rays are reflected at different angles. And so you get this pattern that can be recorded on photographic film. And then by measuring the distance between different dots on the photographic film, you can end up getting the size of the unit for the solid. So it gets much more complicated. It sort of depends. Wave interference is something that happens if you put two waves that are exactly the same side by side. So here you have y1 and y1. They're the same exact waves. And then we have y2 and y2. You can see that if you add them together, on the left, you have constructive interference. Y1 and Y2, their humps overlap at the same point, and so they add together, and you get constructive interference, which means you get a you'll see on the next slide, you get sort of a brighter spot where waves overlap with each other in a constructive way. You look over here for Y1 and Y2 on the right hand side, this is destructive interference, where the trough lines up with the hump, and so they cancel each other out, and you get a much lower wave. And so it's you'll see on the next slide, it kind of comes as a much lighter spot on this. So yeah, here. So if you take the beams, and if they stay in phase with each other, then they're reflected in a certain way, and you get different, you get a response, you get sort of a mark on your on the other side. If they come in and they are, the top one, you can see they're out of sequence. They are reflected and they destructively interfere, and so you don't get you'll get sort of a negative pattern. But in the bottom one, you can see that the waves are in phase, and so they add constructively, and you get a bright spot. Here's sort of what happens. The X-ray beam goes through the crystal, and you get all these spots. So the bright parts are where there's positive interference, and the dark spots are where there's negative interference. And so then they're able to measure angles and distances and things like that, and you're able to get the size of your crystal. Here's an actual crystal diffraction pattern, and you can analyze it. We're certainly not going to get into that. So what should you be able to do at the end of this chapter? Well, you should know what the name of the phase transitions are, like melting, freezing, etc. like that, and be able to describe a heating curve for a compound. So that would mean what temperature, the melting point and the boiling point, what that heating curve looks like. And we know when we have one phase, it's a positive slope. When we're changing phases, the temperature stays constant, and so it flattens out, etc. You should be able to calculate the heat required for a phase change of any substance. Understand how pressure and temperature relate to a phase of a diagram using a phase of a compound using a phase diagram. So remember, a phase diagram plots pressure on one axis and temperature on another, and you can tell if something's in the solid phase, liquid, how it's going to change with respect to temperature and pressure. So just basically being able to interpret a phase diagram, pressure and temperature phase diagram. Be able to identify and describe intermolecular forces. So those are things like dipole-dipole, London dispersion, hydrogen bonding. Determine things like vapor pressure, boiling point, viscosity based on these attractions, being able to know which ones are stronger, looking at molecules like we did, and identify which one should have a higher boiling point, etc. Identify types of solids, and then again being able to tell relative melting points, hardness, or electrical conductivity based on the type of solid. So again, I'm not going to do too much with mixing apples and oranges. They'll be pretty straightforward what we talked about, comparing two ionic compounds with different charges, or comparing molecular with metallic, and which one might have a higher melting point. So that is the end of this chapter.